Good morning. The reason why I'm talking like this is because there's a video lag. And I kind of did a video and I messed it up, and so now I'm doing another one and I'm kind of messing this one up too. But psh, psh. I did my kung fu move because the audio and the video aren't synced up. I'm having a bad tech day today, but let's get this party started, shall we? Section 8.2. Answer the distance and rate problems, and then using the formula d equals rate times time. The distance is equal to rate times time. I don't know if you guys are familiar with that equation, but I'm pretty sure you're familiar with this equation. Rate is equal to distance over time, right? Like, how fast are you going? Well, it depends on how far you went divided by how much time you took, right? That makes perfect sense. So if you guys can hang with this, then you just multiply both sides by t, and you can get distance is equal to rate times time. Are we cool? Yes, of course we're cool. All right, remember I was going to ask you not asking if we're cool because I want to go through this quickly. All right, Jim sprinted down the track at a rate of 20 feet per second. For 25 seconds, how far did he run? All right, straight up, they're just asking. He went 20 feet per second. He went for 25 seconds. What, it's just rate is 20. This is 25. The time is 25. So you just multiply those two and you get, what is it, 20 times 25. Anyone good at that kind of stuff? 500. There we go, 500. Yep, so his distance is 500 feet. Cool. Kawana drove down a highway for 2 hours, and he drove 115 miles. What was his average speed? Okay, so we have the time, check. We have the distance, but this time we're looking for the rate. So what we have to do is we have to solve for the rate, which you both divide both sides by t, divide by t, and you get rate is equal to distance over time. Of course, that's the equation that you already know and love and familiar with, so you just take 115 divided by 2. Anyone can do that in their head really quickly. That would be like, what, 57.5?
Yeah. Nope.
Boom. There we go, 57.5. That's why this is warm-up. It's so easy. All right. Superman threw a ball at a rate of 200 feet per second to someone 3 miles away. How long did it take? So this time, we're switching it up. We're asking for the time, so you would divide both sides by the rate, so you take the distance. I'm going back off of this original equation, so now if I want to figure out my time, I just simply take the rate and divide both sides. And so now I have distance over r is equal to time. So then I take 3 miles, divide that by 200. Well, you kind of got to keep in mind that 3 miles divided by 200. My pen is dying. That sucks. Not only am I having tech issues, I'm actually having pen issues today. Mr. Dalday has issues today. All right. 3 miles divided by 200. You can't just straight up do 3 divided by 2. What you need to do is you need to convert the miles into feet. I think that there are 5,280 feet in every mile, so you multiply 5,280 times 3, then divide that sucker by 200, and you'll get the time. And it'll probably be a very short time because we're talking about Superman throwing a baseball here. Got it? All right, I'm not actually going to calculate that one out. I'm just going to keep on moving on. I love how, or I hate how this thing is so lagged. It makes me feel like a kung fu master. All right, we're going to draw a model of the situation. In fact, what I'm going to do is, I think that what they did was, when drawing graphs to model simulations involving multiple behaviors, it is important to determine the points of the graph corresponding to where the situation changes. The shape of the graph between these points many graphs have complicated or seem complicated but are simply a collection of simple graphs connected together. In this case, only start and end of these different graphs is needed in order to draw the graph. Okay, all right. You're like, Bruce, too fast for the camera. Ah! Yeah, I know. It's funny. All right, let's try this one. Let's see what they're talking about. Alright. We're going to do these tasks and we'll see how well we can hang with these things. I'll do a couple of them for you. And I'll leave some for you guys to play with on your own homework. Sound good? Alright. A ship has plotted a course around an island near the equator. Its course fits the first followed the function f of x equals the third of x plus 3. I'm assuming that f is the distance and x might be the time. Anyway, it stayed on this course until it had moved 3 miles east. It went 4 more miles east with a southern direction defined by the function this. If x represents the number of miles traveled from the start point, and f of x represents the distance north from the equator, sketch the graph. What
I'm confused.
are they talking about? A ship plotted a course around an island near the equator. Alright, got it. Its course followed the function f of x equals 1/3 x plus 3. I'll be honest with you, I don't know what we're talking about here. Let's write stuff down. F of x equals 1/3 x plus 3. When in doubt, write it out. It stayed on course until it moved 3 miles to the east. And then it went 4 more miles east with a southern direction defined by the function. Alright, so this is east. Sketch the graph that and f of x represents the distance north. If x represents the number traveled east from the starting point. Oh, okay. Okay. Okay, I see what's going on. I think I see what's going on. All right. Here's what's going on. This is a terribly written question. I'm just gonna show you. Ready? I think I see what's going on. Okay. So, all right. So we're talking about a ship, right? And we have a little coordinate system here.
Nice ship.
Yeah, it's a triangle ship. This is a terrible pen. What's going on? This was my good pen, too. Mr. Dalday has issues today. I'm so disappointed. Ship. Ocean.
Cute, man.
North, east, south, west. Ship moves at 1/3 x plus 3.
Ship moves what?
The ship moves at 1/3 x plus 3. So they were saying that f of x, this is f of x, and this is x, right? So right now, it's moving north as a function of x. So as it goes out this way, it moves north. Does that make sense? So the direction that the ship is actually going it's going to be going like that, in that direction. We cool? I know it's hard to see. I'm sorry. The black pen doesn't work. This red pen doesn't work. The blue pen might not work. Can you guys see that better?
No, it's not the same as the web.
Yeah, let me me just do this. Maybe the glare will go away. So, you have a ship. Never eat soggy waffles. And the way this ship goes is it's going to kind of go in this upward diagonal direction. For every x you come out, it actually goes north a little bit. Okay? And I'll show you what I mean. Let's try this. At x equals 0, what is f of x? Okay? At x equals 0, what is f of x? Well, if you plug in a 0 here, you have 0 times a third plus 3. Oh, that's 3. So, at 0 miles east, it is already 3 miles north. That's where the thing started at. Are we cool?
Yeah.
And then they said, all right, now what I want to do is, what about 1 mile east? Okay, fine. You just plug in x equals 1 into here. So 1/3 times 1 plus 3 is 3 1/3. So that's what, like 3.3? So it's kind of like up here a little bit. Are we cool? So this is 1 mile, 2 mile, 3 mile, 4 mile. So you're about 1/3 of the way up there. At 2 miles away, you just plug in 2 and you'll get up to here. And at 3 miles away, you plug in 3 into here and you'll have 1/3 times 3, which is 1, plus 3, which is 4. So you'll go up to 4. We cool? So this is the direction that they traveled. Got it?
Yes. Got it.
All right. Then what they did was they actually turned the ship and they traveled south, but they kept going east. So what I mean by that is south is going this way, east is going this way, so they kind of went in this direction now. Cool? Yeah, so maybe they're over here in Ocean, and then they went over to Hawaii. And then they're like, sweet, I'm done with Hawaii, now let's go over to, I don't know, like South America. Right? So they're going to kind of go in this direction down like that. Cool? So here's the way the function that they describe over here. Now at this point, we're using this function right here. So let's plug in 4. Okay? Because I want to figure out, I want to keep going this way. So if I plug in 4 into there, how would I, oh, yeah, okay, that works. So that would be plug in 4 into here, and you have -2 times 4, which is -8, plus 10, which is 2. So it goes down to 2. So this is the graph that they have for the last bit of their trip. Are we cool? So then you can figure out, basically I only need 2 points to make a graph. I know one of these points, and I know this other point. And I can just say, all right, there we go. Or if you want 2 actual points, what you can do is you can plug in x equals 5. If I plug in x equals 5, then I'll plug it into this equation, because at this point I'm using this equation. So I have -2 times 5, which is -10, plus 10, which is 0, and so that's why it crosses right at 0. Have you noticed that?
Yes.
Are we happy?
Yes.
I apologize for the ghetto version of how ghetto this computer is treating me, but you know, I mean, I'm doing the best I can. All right, let's keep going. Let's get away from. I'm glad I did that one for you because that one was dumb. Let me just make sure. I'm going to read this problem right here just to make sure that it's not as dumb as the other ones. Ready? A shipping container has dimensions 8 feet tall by 8 feet wide by 20 feet long. The first quarter of the container takes 10 minutes to load, but it only takes 20 minutes to finish the rest. The shipping container is loaded, but someone forgets to lock the door shut. When the crane lifts it to the ship, 5 minutes later, all the contents fall out in about 60 seconds. What a bunch of idiots. Sketch the graph of the volume of the ship. Okay, all right. So what you noticed here is that these slopes over here is actually the rate at which they're going. It's the how far it's changing as a function of time. You guys get that? So what's going to happen is, I'll show you how this graph looks. So it will probably, and here's the thing is, I want you guys, I'm going to show you just kind of generally how I think it might look, and then I want you to actually fill in the nice exact answers and make the graph all pretty and stuff. But if I have my graph here, okay, and this is what? All the way up here is full. Full. And then this is half full, and this is quarter full, 3/4 full. You guys get it? And then over here, this will be 10 minutes, 20 minutes, and then 1 minute right after that. Okay. 10 minutes, it's a quarter full. Boom. Boom, so you can actually see it. All right? In 20 minutes, so that'd be from here to here, it is full. Boom. Got it? Then they waited 5 minutes, so that would be not 10, but half there. Picked up the container, everything fell out, and so now it's 0 full in about 1 minute. And everything broke because they picked up a container and everything fell out. So like all these plasma TVs that we loaded just broke. Somebody got fired. All right, we cool? And actually, to be honest with you, I think I actually even did the whole problem for you. You kind of gotta tell me with the exact numbers over here, but I pretty much did that one for you. We're good. All right, let's look at this one. How much time do I got? All right. I don't have a whole lot of time. Do you guys feel like you guys have trouble with this homework, or have you guys tried this one yet?
I haven't tried it.
All right. Let's try this one. Sarah drove along the highway 60 miles per hour. That's 1 mile for every minute. That makes sense. For about 6 minutes until she reached a town that was stopped by construction work. She had to wait 2 minutes until she drove off at 30 miles per hour for another 4 minutes until she reached her destination. Draw the graph of her velocity versus time graph. Ooh, I like these problems. If we're talking about velocity versus time graph, what we're looking at here is she drove at what velocity? Well, up here is 60. This is 30. She drove at 60 miles per hour for 6 minutes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for 6 minutes, 1, 2, 3, 4, 5, 6, somewhere around 1, 2, 3, 4, 5, 6, somewhere around here. She was going at a constant 60 miles per hour, right? Then she hit construction work. She had to wait for 2 minutes. So for 2 minutes, this graph, what is her velocity now?
0.
0. She dropped down. Dropped down to 0 miles per hour. All right? Then she went for 4 minutes at 30 miles per hour to reach her destination. We cool? All right. So now, what does her distance time graph look like? So let's do this. Let's go 1, 2, 3, 6, 2, 6. All right. So here's my question. Your distance time graph is going to look a little different from this other time graph, right? Now, no, it's not going to look the same. It's going to look different. At time equals 0, how far away is she? Say that she started over here at the house. And she drove. At time equals 0, how far away is she from the house?
She's 60 miles.
She's 60 miles away?
Yeah. Wait,
At
no,
time
did you say
equals
0? No, she's at the house.
Okay, wait, yeah. So you and I are hanging out, right? And you just be like, I gotta go. I'll see you later. And you're driving 60 miles per hour. And I'll be like, all right, bye. And as soon as I say bye, you're saying she's 60 miles away
No,
already?
I thought you meant at the 60
Dude,
minute.
is she like in Star Trek and she's just traveling and like
Yeah, she like.
see ya,
like
beat me
beams.
up. There I go. No way. At time equals 0, you're 0 miles away, right? All right, good. Now she drives for 6 minutes at 1 mile per minute, because that's what 60 miles per hour is, really, right? How far away is she now? You can answer. You can. Don't be afraid. Just because I ridicule you in front of all of your friends and peers.
What was the question?
There we go. 6 miles, Justin. Awesome. Because 6 minutes later, 1, 2, 3, 4, 5, 6. She's up at here at 6 miles per hour, or 6 miles away. This is the distance time graph. Now, for 2 minutes, say that she's 6 miles away. Got it? She hits construction. And 2 minutes later, where is she?
She's constant. No, I mean she's just like she's dead.
She's dead.
She's just dead.
The distance is flat. Exactly, Justice. Because for 2 minutes, at the beginning of minute 6, she's at 6 miles away. At minute 7, she's still at 6 miles away. At minute 8, she's still at 6 miles away. So it's this constant spot right there. Got it? Then, right, and she's waiting. And then after that point, she goes up. But here's the thing about this one is she doesn't go up as fast as she went up the...
She goes slower.
She kind of goes at a slower rate. So what I mean by that is the slope of this line is steeper than the slope of this line. Can you guys see that?
Mm-hmm.
Now actually what this tells you is this value right here tells you the slope of that line. Interesting, huh? Nah, you guys don't care.
No, it's interesting.
Yeah, exactly. The velocity time graph tells you the slope because the slope of a position time graph is the velocity that you're moving at. I mean, if you think about it, the position time graph, right? I talked about the slope. What is the slope? The rise over the run, right? Rise over run is how high you change divided by how far you change. How high you change depends on the distance you go, right? Your change in distance divided by your change in time. Hey, wait a second. Distance divided by time. That's velocity. That's why this graph is totally related to this graph. Does that make sense to you? Did that blow your minds or did that cool? We're good. I'm happy. You blew my mind. And I hate to say it, but I think we have to finish class. I got to start the physics class in 2 minutes. All right. So here's what I'm going to do for you. Since I had such a terrible issue with all of this kind of stuff, I think I made something do. All right, let me see. Let me take a look real quick. In the class, I made functions 8 through 14, page 8 through 14, due on Friday. And we got up to page 14. Okay, that sounds fair. You guys should be able to do that, because I just lectured up to page 14. All right, see you guys later.
All right, bye.
Okay.